We're very briefly going to introduce the idea of the boundary layer. Now, if you remember from our discussion of inviscid flows, we talked about D'Alembert's paradox. And the idea was that theory, based on Euler's equation, predicted no drag, even when experiments showed that there was drag. And then the experiments showed that there was drag even for flows that should be able to be considered inviscid. And this was a big problem for fluid mechanics because we couldn't explain drag. And this lasted until about 1904 when Prandtl came up with this idea of the boundary layer. The idea was that he divided the flow into two regions. He said, far away from a surface, the flow is basically potential flow, and you can solve that using Euler's equation. However, very near the surface, we have this thin layer where viscous effects are still important. And this layer arises because of the no-slip condition. The flow on the surface of the object has to have a velocity of 0. So we have this thin region with viscous effects that's on the boundary of the flow, which is why it's called the boundary layer. Now, this was a very key link between theory and practice. It allowed us to unite the idea of hydrodynamics, which was based on Euler's equation, and hydraulics, which was based on basically empirical laws or equations developed by practicing engineers. It introduced the idea that we could finally explain why this drag force existed. So it created a theoretical framework for that drag force. This allows us to solve problems that are actually too complex to solve otherwise. It's very difficult to solve the Navier-Stokes equation for most problems. We actually developed these equations in 1827, and for turbulent flows we still don't have a very good general solution method for solving the Navier-Stokes equations. What boundary layer theory does is it allows us to solve Euler's equation in the main flow, which is much easier to do, and then only apply the Navier-Stokes equation in the boundary layer, so we only have to solve that more difficult equation over a smaller area. Now, we're going to explore boundary layer theory by looking at a very simple case. We're just going to look at flow over a flat plate. Now, this has applications to aircraft, submarines, and many other fields. And it's characterized by the form of the Reynolds number that's shown here, where we have x, or the distance from the leading edge of the plate, as our length scale, and capital U is the velocity far away from the plate, and that's our velocity scale. Now, all boundary layers start out as laminar, as you can see in the graph here, the picture, but then we have a transition region, and then the flow becomes turbulent. Now, the transition, the location, is affected by many factors, and it could include pressure gradient, the roughness of the surface, whether there's any heat transfer present, or various other things. For now, we're not going to concern ourselves too much with turbulent boundary layers. We're just going to look at laminar boundary layers. And then later on, we'll take a closer look at what happens when the boundary layer becomes turbulent. The first question we have to answer is, how can we define the boundary layer? We can't generally just use where the velocity equals the free stream velocity, because some models are a little bit shaky near that boundary. So the most typical definition we use is called the displacement, or the disturbance thickness. The disturbance thickness is the distance from the surface where the velocity reaches 99% of what we call the free stream velocity, or the velocity far away from the surface. But we can also define a couple of other versions of this. The first one is the displacement thickness, or delta star. And the idea here is, if you have a boundary layer, you actually reduce the mass flow rate, because you have this region here where the velocity is lower. And the displacement thickness is basically how far you would have to move the surface to maintain the same mass flow rate in this region as you have in this region. So essentially, the area here is the same as the area here. We also have the momentum thickness, or theta. Now, this idea is the same as for the displacement thickness, but instead of mass, we're looking at momentum. So the idea here is it's the distance that this surface would have to move to maintain the same momentum flux as the real case if the flow were inviscid. So it's based on the same idea as displacement thickness, but we have a different quantity of interest. Now, the momentum and displacement thicknesses are both what we call integral thicknesses. It's easier to measure these than it is to measure the disturbance thickness. So that's why we've defined these parameters, and then we can compare the results with experimental data. There is a physical significance for each one, which we'll explore a little bit later. And it's important to notice that these integrals are basically zero outside of the disturbance thickness, so we can limit this limit of integration from 0 to delta. Now, the flat plate is a good approximation for a lot of problems. Flow is developing, the surface is nearly flat. In this case, nearly flat means in relation to the boundary layer thickness. So the surface is either long or flat in relation to delta. Now, that may not seem particularly long or flat to us, but the boundary layer is very thin. So a lot of times we can approximate ship or submarine hulls, types of aircraft, even the surface of planet Earth as a long flat plate. The boundary layer begins to form at the leading edge of the plate, where x equals 0, and it starts out as laminar. And we can look at this with the Navier-Stokes equations with some engineering simplifications. We assume that at delta, the velocity is equal to the free stream velocity. We also assume that the gradient is 0. So du dy is equal to 0 at y equals delta. We're going to make an assumption that v is much, much smaller than u in the boundary layer. So a lot of the times we just ignore the y direction velocity. We only care about the x direction velocity. And we're also going to assume that the boundary layer is very thin, so that the pressure is the same everywhere in the boundary layer. dp dy is 0. Pressure can still change in the x direction, but not in the y direction. So simplifying this Navier-Stokes equation using these basic ideas gives us these equations. The other conversion we've done is we've replaced the pressure term with this u du dx. So it's no longer dp dx, it's u du dx. And we get that from the Bernoulli equation for the inviscid region outside the boundary layer. So to solve this set of equations, we assume that the velocity is a function of this parameter eta. Now, the math gets complex. That's why we want to use what we call a similarity variable, which is what we call eta, the similarity variable. And this comes from dimensional analysis. We also don't want to solve directly for this function f because of the complexity of the solution. So what we do first is we solve for capital F, and then we integrate that to find the actual f that determines the velocity. So with these simplifications from the Navier-Stokes equations, a guy named Blasius derived a set of equations and boundary conditions that we could then solve for the velocity profile in a laminar boundary layer. Now this result is important because it was able to convert the PDE into a much less complex ordinary differential equation. However, there's still no analytical solution to this problem. We have to solve it numerically. So when you solve it numerically, you end up with something that looks like this, and the line on this graph is the theory based on Blasius' solution. And the points are experimental data that was collected for various laminar boundary layers. And you can see that the experimental data almost exactly matches the theoretical prediction here, which is a good result. There are two important results from this. The first is if you look where the u over u is 0.99, we get that delta over x, which is our boundary layer thickness, is 5.0 over the square root of Reynolds number. So you can see that eta is 5.0 where this ratio is 0.99. And so that gives us a model now for the thickness of a laminar boundary layer. The second is an equation for the velocity gradient where y equals 0. So by solving Blasius' equation, we now have the gradient of the velocity at the surface. And from that, we can use Newton's law of viscosity to give us the drag on the surface. And this is, in dimensionless form, we use the skin friction coefficient. So tau at the wall is the wall shear, force per unit area, and CF is the skin friction coefficient. Then we can integrate this from 0 to some position L along the plate to get the drag coefficient. And so now we can get the drag force. The integral of shear over area is the drag force. So now we have an equation for the drag force on a flat plate with a laminar boundary layer. Now this model works well for laminar flows that are what we call self-similar, where the profile doesn't change, U over U doesn't change with X. But the question is, what about turbulent flows? And what if U varies with X? How will we be able to solve for those types of boundary layers? And we're going to need to use a new approach, what we call the momentum integral approach. And we'll talk about that in a few minutes. It's also important to understand some limits. If we look at the graph, we have this converging and then diverging nozzle. In this case, the flow is not what we call self-similar. dp dx is not 0, and the free stream velocity is going to change with x. So if we look in region 1, the flow is accelerating. So the velocity is going to increase and the pressure is going to drop. We call this a favorable pressure gradient. This pushes the fluid in the boundary layer along and actually helps accelerate it and helps maintain a stable boundary layer. In the second region, the flow speed is constant. So our velocity is going to be constant and the pressure gradient is going to be 0. So then it would be like the Blasius solution. And then in region 3, the flow is decelerating. And because of that, the velocity is decreasing, and so the pressure is going to increase, which we call the adverse pressure gradient. Now, the fluid is all decelerating, but in the boundary layer, we have pressure, force, and friction. So the fluid in the boundary layer is decelerating much more quickly than the fluid outside the boundary layer. And it also starts with a lower speed than the main flow. So eventually, the fluid in the boundary layer can completely stop. What I mean by that is that the velocity gradient at the wall is 0. du dy equals 0 at the wall. Beyond this point, you can have backwards flow right near the surface. In this case, the boundary layer is no longer attached to the wall. It actually starts a little bit away from the wall. And that's what we call boundary layer separation. Now, this is possible under conditions where we have an adverse pressure gradient, but it's not always guaranteed. And it implies that the wall shear is 0, mu du dy is 0 at the surface.